So yesterday, we talked about projectile motion in general, and we went specifically over, okay, questions where the object was projected horizontally. Okay, what's the big thing we have to remember about an object that's projected horizontally? Okay, so one of the things we have to remember is that the horizontal velocity, whatever it is, let's say it's 8.0 meters per second, is constant. Okay, so for the horizontal part, okay, we are talking about V equals D over T. All right, it's a constant velocity thing. Okay, there's no forces to slow it down because we're not considering air resistance or anything like that. Okay, what else do we have to remember? Okay, so it has two dimensions, the horizontal part as well as the vertical part. Okay, so the horizontal part is constant velocity, but the vertical part is what kind of motion? Accelerated, right, and because of gravity. Okay, one other thing we have to remember about the vertical part, and this only applies to objects projected horizontally. It starts with a vertical velocity of 0. Okay, those are the things. Okay, so this here and this here, that applies to any kind of projectile motion. Projected horizontally, okay, projected at an angle, which is what we're going to look at today, right? But this is the key to horizontally projected projectiles, is that their initial vertical velocity is 0 because they were thrown horizontally, okay, and they were not moving vertically at time 0. Everybody follow there? All right, so we went over the 3 kinds of problems you can have with this. One's where you're asked to find the height of the cliff, or where you're asked to find how far from the base of the cliff it travels. In other words, its horizontal displacement, or asked to calculate its projected velocity at the beginning. All right, those are really the only 3 ways that a problem like that can be asked. So today, we're going to look at ones like the fake speed bus jump that we looked at yesterday, where a projectile is projected at an angle. All right, so for projectiles projected at an angle, they are like any other vector quantity. This is a velocity. We'll just say that in this particular case, this thing was projected at 100 meters per second at 30 degrees above the horizontal. Okay, so that's like, maybe it's like a, human cannonball shot out of the cannon. Okay, 100 meters, but that'd be pretty fast for a human cannonball, but let's just say, okay, 100 meters per second, 30 degrees above the horizontal is the velocity they come out of the cannon at. All right. In the perfect physical world, they will follow a projectile arc that will re-encounter the ground over there, some distance away. That distance is affected by essentially 2 things: the projected velocity and the angle. Right? You guys, if you ever played with a hose as a kid, right? You got the hose on and the water only goes so far, but if you angled the hose up a little bit, the water would go farther. Okay? Well, that's because of angle. It's just a projectile motion. Okay? Water coming out of a hose is still a projectile. Okay? Every single water molecule coming out of that hose is an individual projectile. Okay? And off it goes. Everybody kind of follow on that? Okay. So if we're looking at this type of projectile, we still follow a lot of the same rules we followed for ones projected horizontally. We still break it up into its vertical and horizontal parts. Okay? And we'll be asked similar things. Okay? With the projected horizontally ones, sometimes we were asked how far from the base of the cliff would they hit the ground. In other words, how far would they travel horizontally? Well, I might be asked that question for this. How far would this object travel horizontally? Right? I might also be asked, what's the maximum height of the object? Right? Because now, because we're projecting it slightly upwards, it's going to go up and come back down. Right? So I would need to know, especially if this was a human cannonball being done indoors, okay, the maximum height would be kind of important for the safety of the human cannonball. Agreed? So things like that, right, would be things that we would have to calculate. So we're going to break it up into its vertical and horizontal components. So at time 0, human cannonball is just coming out of the cannon. Okay, this is how fast he or she is moving and the angle they're moving at, which means that this velocity vector here has a horizontal component and it has a vertical component. Right? Now we've already said that horizontally the velocity won't change. So that means that if I find this side of the triangle, that's supposed to be a z. Okay, that's going to be the horizontal velocity. Okay, because this thing is moving horizontally and upward at the same time. So when I find this side, the horizontal component of this, that will be my v horizontal. Okay, that velocity that will not change throughout the entire flight. So what does that mean the red side is? Remember, this is at time 0. So this would be the what velocity? VI. This is going to be the initial, because this is how fast, this is the beginning of the problem. Okay? We know that the velocity vertically is going to change because gravity is going to slow it down and then bring it back to Earth. All right? So it's going to go through that. So if we're looking at a projectile motion problem from those two perspectives, if I'm only looking at the horizontal part, okay, then I just see an object traveling in a straight line at a constant velocity. If I'm watching it only from a vertical perspective, all I see is an object goes up and down, and that's it. Okay, combined together, we get this arc. Okay, but separately, that's the two motions that are involved. All right, so if I want to calculate my initial vertical velocity, okay, that's the opposite side of this triangle, agreed? So just like finding x and y components from vectors before. So I would take the sine of 30 degrees and multiply it by 100, and that would give me 50 meters per second. And I'm going to make that positive because it's up. Okay, I know the acceleration is negative 9.81 meters per second squared. We didn't make that negative in the ones we did yesterday because there wasn't a change in direction. There is now, so now we have to indicate that. Okay, I know one other thing. The question doesn't outright tell me this, and there's not really a way for me to calculate it either, but I just know it. And it's the final velocity. What's the final velocity of the human cannonball? See, that's what everyone says, and I kind of set you up there, sorry, Don. Okay, we all think 0 because he's going to hit the ground and stop, except that we're actually looking for what's his velocity the instant he hits the ground, before the ground slows him down and they become a puddle. Okay, so we want to have something that tells us what's that final velocity. Now, yesterday we said that if I throw something up in the air and catch it at the same height I threw it from, it would be going the same speed, right? And remember, even though this is doing an arc, all it's doing from a vertical perspective is what we drew yesterday, up and then back down. So whatever it moved at initially is what it comes back at in the other direction. So if VI was positive 50, VF is negative 50. Okay, it's going to come back down at the same velocity vertically that it was shot at. Okay, so our horizontally projected projectiles, the one thing we had to memorize was that VI was going to be 0. Okay, for these, we have to memorize that VF is equal to VI. Okay, if we're talking about the whole trip, and also if the launching point and the impact point are the same height. Okay, so we're on a perfectly flat stretch. Okay, then yeah, it makes a difference. Right, but if I'm doing this from the top of a building, okay, it's a little tougher because it's going to fall the additional height of the building on the other side. We don't do very many like that, so you don't need to worry about it for now. All right, so I have that information vertically. Then I need to calculate my horizontal information. And there's only one thing right now that I can calculate horizontally, and that's my horizontal velocity. It's the adjacent side on that triangle. Okay, so V horizontal is going to be the cos of 30 degrees times 100, so it's going to be like 86 point something. 86.603. Meters per second, and we know that that's going to be constant. Okay, so that's what we know at the beginning of a kind of basic projectile motion problem. The things you'd be asked to calculate would be the distance traveled horizontally and the maximum height vertically, okay, in a basic question. In order to calculate either of those things, what do I probably need first? Time. Okay, remember we said yesterday in all projectile motion problems, you're always looking for time. Okay, can I find time with the information I have? I can. I can use my formula from Science 10 even. Okay, I can use A equals VF minus VI over T. So if you're ever lost, look for time. Okay, that's probably your best bet as a first step on a projectile motion problem. So T is going to equal negative 50 minus 50. Okay, so final velocity minus initial velocity over acceleration, negative 9.81. Okay, so I'm going to have negative 100 divided by negative 9.81. So this thing's going to be in the air for 10.19 seconds. All right, can I apply that time over to the horizontal part? Okay, so that's the other thing we have to remember. Okay, that applies to all of them, is that the time is the one thing they share. Okay, can I now calculate how far this thing travels horizontally? Right, I have the horizontal velocity, which is constant, and I have the time. So I can calculate the total distance or displacement horizontally of that object. Okay, D equals V times T, so 10.19 times 86.603. Oh, 6025. All right, it's going to travel 882 meters. I only have two significant figures here, so it'd be 8.8 times 10 to the 2 meters. Okay, so that's pretty far. It's definitely not a human cannonball. Okay, you don't fire a human cannonball 800 meters. Yeah, at 100 meters per second, that would definitely be very hard on their body during the launching process. Okay, all right, so now we figured out how far it goes horizontally. Okay, and we've done that by calculating the time. The other thing you might be asked to calculate would be the maximum height of the object. Okay, where does the maximum height of the object occur? Okay, if I'm following this arc, where would the highest point be? Beginning, middle, end? In the middle. Okay, the highest point is going to be in the middle. All right, so here's what I have to understand about that highest point. From a vertical perspective, how fast will the object be going at that point? 0. Okay, when you throw something up in the air, at its highest point is where gravity has slowed it down, and stopped it instantaneously before it starts to fall back to Earth. All right, so we would know that here at the maximum height, VF would be 0. VI is still 50. Acceleration is still 9.81. So if I have VI, I know VF, and I have A, can I find D? Right? I'm looking for the vertical displacement when VF is 0 here at its maximum height. So VF squared equals VI squared plus 2AD. Right? I have all of those except for D, so I can use that to find my maximum height. Right? So I'm going to manipulate for that. So I'll have VF squared minus VI squared over 2A equals D. All right, so when we plug in our numbers here, that's going to be 0 squared minus 50 squared divided by 19.62, negative 19.62. That's 2 times 9.81. Negative 19.62. All right, so he's going to reach a maximum height of 127 meters. We only have two significant figures, so we would write 1.3 times 10 to the 2 meters. It's pretty far to fall. Yeah, definitely not a human cannonball question. All right, so does everyone kind of follow what we did there? Okay, again, we follow the same principles. Break it up. Treat the two dimensions separately except for time. Okay, use the information that you can find to solve for the things you're looking for. Okay. All right, so we're going to look at a few examples of like real projectile motion. Okay? And then we'll do a couple of problems and we'll look at a few more. So I got a few more videos to show you. Yesterday was video heavy. Today is going to be a little more video heavy too. Okay? Got a few to look at. For the video we just watched, okay, the General Lee is jumping the riverbed. We know the following things. The speed of the General Lee is 32 meters per second when it leaves the ramp. That's around 120 kilometers per hour. Okay, the ramp is angled at 20 degrees above the horizontal. We are looking for what distance across the river and the maximum height of the General Lee in this jump. Okay, so we don't know how far it comes crashing down from. Okay, so I'll give you a few minutes to get that set up, then I'll set it up and I'll give you a few more minutes. Okay, so our setup goes as follows. Okay, this line, the projected velocity of the General Lee, is 32 meters per second. The ramp it jumped from is 20 degrees above the horizontal, and it followed a projectile arc that re-encountered the riverbed on the other side. Okay. So we have to remember that this side here of that vector's triangle, or the x component, is going to be the what? This is the horizontal velocity, right? Okay, and then this side here is going to be, what's this side going to be, guys? It's going to be initial vertical, right? Okay, I'll leave you to it there. So as with all projectile motion problems, we first want to break it up into its two components, horizontal and vertical. Okay, and then we want to calculate as many pieces of this puzzle as we can. Okay, first thing we're going to calculate is VI. Right, it's the opposite side of that triangle, so VI is going to be the sine of 20 degrees times 32 meters per second. Okay, so VI is going to be 10.94 meters per second, and that's up. So what's VF then, if we're talking about the whole trip? Negative 10.94, okay, because when it comes back down on the other side, it's the same height as the side it was launched from, okay, so we have 10.94 negative meters per second. All right, then we can calculate the horizontal velocity, V horizontal. It's the adjacent side, so we're going to go cos of 20 times 32. All right, so we got 30.07 meters per second there. All right, and we know that's not going to change. It's going to travel at 30.0 meters per second horizontally the entire flight. If I am going to calculate the horizontal displacement of the General Lee, that is how wide the riverbed is, what other thing do I need? Time. All right, and I can calculate that with my vertical information here, so that's my next step, is to calculate time. Time will equal VF minus VI over A, so that'll be negative 10.94 minus 10.94 over negative 9.81. Okay, and we'll divide that by negative 9.81. All right, so we got 2.23 seconds. So it's in the air for 2.23 seconds. And I know in the video it seemed longer than that, but remember, it was in slow motion. Okay, so if it was in real time, it would have been 2.23 seconds. That I can bring over here because time is the one thing that these parts share. So now I can calculate D because I know the speed at which, or the velocity at which it's moving horizontally, and the time. So I take my 30.07, multiply it by 2.23, and I will have the width of the riverbed. Okay, so the riverbed is 67 meters wide. Okay, so if you're looking at like our running track out back, that's 2/3 of the length of one straightaway that it would have jumped through the air. Okay. It would be about the equivalent of if you went down 32nd Street to the Sheep River and you jumped the entire bridge. about 67 meters. Okay, be about like that, which would be impressive if you were there watching it. Then, of course, you have to call an ambulance and fire trucks, and it'd be bad. Okay, that's the first thing we were asked to find. The second thing we were asked to find was, what was the maximum height of the General Lee? So how far above the river was it at its highest point? So what we have to remember there is that VF is 0. Okay, the other thing we need to know is none of the horizontal information can help me with that calculation other than time. If I use the horizontal information to get time, but okay, I can't use anything from the horizontal part to tell me about the vertical displacement of the General Lee. All right, now what we usually do here is we go to, all right, we know VF is 0 at this point. Okay, we know VI is still the negative, or sorry, the 10.94 that we calculated before, and we still know the acceleration. So because of that, we can use this formula. But I oftentimes have people try this, and they go D equals VI times T plus 1/2 AT squared. And what do they use for time? We know the whole trip took 2.23 seconds. When does the highest point occur? Halfway, right? You can do that, but for some reason, people don't do it right when they do it. Okay, it's a perfectly valid way to solve this problem and should arrive at the same answer. But what I find is for some reason, people don't do it right, okay, when they're doing it. I still have not figured out exactly why. Okay, but I know that this VF squared equals VI squared plus 2AD works more often. Okay, people just seem to manipulate that equation better or whatever it is. Okay, I mean, this shouldn't require any manipulation, but somewhere along the way, people mess something up. Most of the time, I think is they forget to make the acceleration negative, but I mean, that could happen here too. Okay, or they forget to square time or something. And so anyway, we're going to use this method because it seems to work more often, and we have those formulas there. So D is going to equal VF squared minus VI squared over 2 times A, so that'll be 0 squared minus 10.94 squared divided by 2 times negative 9.81. So we'll get the maximum height of the General Lee here. So okay, it's going to reach a height of 6 meters. That will be roughly the equivalent of dropping a car off the top of the gym. It probably wouldn't go well for the car. Okay, so 6.1 meters is the maximum height of the General Lee. Okay, now kind of just looking at using this formula here, okay, we should be able to use that formula to calculate at least a very similar number. We would have our 10.94 here multiplied by how much at the time? Half. Okay, so we would need to take our 2.23 there. Okay, and get our new time, so 1.11. Okay, plus 1/2 times negative 9.81 times 1.11 squared. Okay, so we should get, okay, a similar number here. Okay, get the same answer. I just don't know why people don't get it right when they do it. Okay, it's a perfectly valid way to get the vertical displacement, but as I said, for some reason people don't get it right, and I don't know whether that's because they forget to square the time or what they do wrong. Okay, but as you can see, I got exactly the same answer using both methods, and that's exactly the way it should go. Okay, so you can use either method. You should arrive at the same answer either way. You may. All right, so now we're going to go back to the Mega Whoosh thing. Okay, so we watched the Mega Whoosh video yesterday where the guy shot himself, supposedly, into that tiny kiddie pool, which seemed to not move at all when he landed in it, which is what totally sold it as being fake. Okay, now we'll look at how Adam and Jamie bust that one. Okay, they go into a lot of effort to do this, and then they build what looks like the the most fun thing ever. Okay, they build that whole slide right next to a lake. Okay, which is like really cool. So, okay, we'll give that one a try.